scientists discover ingredients for life just beyond our galaxy. In recent years, mounting evidence has shown that the ingredients for life, in the form of complex organic molecules, COMs, form in stellar nurseries and protoplanetary disks. In a recent study, a team led by scientists from NASA's Goddard Space Flight Center, GSFC, confirmed that COMs can also be found around young stars outside of the Milky Way. Using data from the James Webb Space Telescope's mid-infrared instrument, MIRI, the team discovered 5 different carbon-based compounds in the Large Magellanic Cloud, or LMC, our nearest galactic neighbor. Marta Sawillo, an astronomy professor at the University of Maryland and a research scientist with the Exoplanets and Stellar Astrophysics Laboratory and the Center for Research and Exploration in Space Science and Technology at NASA Goddard, led the study. She and her fellow GSFC researchers were joined by colleagues from the Laboratory for Astrophysics at the Leiden Observatory, the Osservatorio Astronomico di Roma, Leonard Jones Laboratories, the National Radio Astronomy Observatory, or NRAO, the Max Planck Institute for Radio Astronomy, or MPIFR, the Institute of Physics at the University of Cologne, and the Southwest Research Institute, or SWRI, and multiple universities.
Based on data obtained by MIRI's medium-resolution spectrograph, Sawillo and her team identified 5 COMs in the ices surrounding the young protostar ST6. This included acetaldehyde, acetic acid, ethanol, and methylformate, all of which have applications here on Earth. Whereas methanol and ethanol are common types of alcohol, methylformate and acetaldehyde are used primarily in industrial chemicals, while acetic acid is the main component in vinegar. These molecules have all been detected in stellar nurseries and protoplanetary systems within our galaxy. However, this was the first time that ethanol, methylformate, and acetaldehyde were detected in a neighboring one. In addition, acetic acid has never been conclusively detected in ices in protoplanetary systems until the release of this study. As Sawillo explained in a University of Maryland news release, modeling and chemical experiments have shown that COMs form in the gas and ice phases of interstellar dust grains through a series of chemical reactions. In addition, previous observations have revealed gas phase methanol and methylformate in the LMC. Said Will Rocha, a researcher from Leiden University and a co-author on this study, our detection of COMs in ices support these results. The detection of icy COMs in the Large Magellanic Cloud provides evidence that these reactions can produce them effectively in a much harsher environment than in the solar neighborhood.
What is especially significant about this discovery is the environment in which the COMs were detected. Located about 16,000 light-years away, the LMC has roughly 1/3 to a half of the heavy elements present in the Milky Way and experiences much higher levels of ultraviolet radiation. This makes the larger of the 2 Magellanic Clouds a perfect environment for studying star formation during the early universe. Roughly 100 to 200 million years after the Big Bang, the first population of stars in the universe, population 3, formed from the only elements that existed at the time, hydrogen and helium. Stellar models suggest that these stars were very massive, up to 1,000 solar masses, emitted large amounts of UV radiation, and were short-lived compared to subsequent populations. The fusion of hydrogen and helium in their cores produced heavier elements such as carbon, oxygen, nitrogen, silica, and iron. When these stars reached the end of their lifespans and went supernova, 2 to 5 million years later, they shed their outer layers and dispersed these elements throughout the universe. Said Sawillo, the low metallicity environment, meaning the reduced abundance of elements heavier than hydrogen and helium, is interesting because it's similar to galaxies at earlier cosmological epochs. What we learn in the Large Magellanic Cloud, we can apply to understanding these more distant galaxies from when the universe was much younger. The harsh conditions tell us more about how complex organic chemistry can occur in these primitive environments, where much fewer heavy elements like carbon, nitrogen, and oxygen are available for chemical reactions. The detection of icy COMs in an environment analogous to the early universe indicates that the building blocks for life formed much earlier than previously thought, and under a wider variety of conditions. The team also observed spectra that indicated the presence of glycolaldehyde, a carbon-rich molecule similar to carbohydrates. This COM is also a precursor to more complex biomolecules, including components of RNA. However, this particular finding will require further investigation before it can be confirmed. What's more, the team's findings suggest that the COMs they detected could survive the early stages of planet formation, when dust and gas from a protoplanetary disk accrete to form larger bodies. This process leads to accretion heating, in which material becomes increasingly compressed under its own gravity, thereby heating up. These results suggest that COMs predate planet formation and are assimilated later on early planets, eventually giving rise to life. Sewillow and his team hope to expand their search to include additional protostars in the LMC and the Small Magellanic Cloud. We currently only have one source in the Large Magellanic Cloud and only 4 sources with detection of these complex organic molecules in ices in the Milky Way. We need larger samples from both to confirm our initial results that indicate differences in COM abundances between these two galaxies. But with this discovery, we've made significant advancements in understanding how complex chemistry emerges in the universe and opening new possibilities for research into how life came to be. It's all thanks to JWST's exceptional sensitivity combined with high angular resolution that we're able to detect these faint spectral features associated with ices around such a distant protostar. The spectral resolution of JWST is sufficiently high to allow for reliable identifications. Before Webb, methanol had been the only complex organic molecule conclusively detected in ice around protostars, even in our own galaxy. The exceptional quality of our new observations helped us gather an immense amount of information from a single spectrum, more than we've ever had before.